Okay, in this last video, I want to talk about how we can put these ideas together to solve non-homogeneous linear systems, and then maybe run through an example of this. Okay, so yeah, solving non-homogeneous systems. From a high level point of view, we'll get into the nitty gritty certainly in the coming weeks. So we talked about how to solve homogeneous systems to find the general solution. Now we want to talk about solving non-homogeneous linear systems. So what am I talking about? Well, remember, we have x prime is equal to px now plus a non-zero f right here, okay? Where f, is not zero in this case any longer. This is our system of ordinary differential equations. Now, the steps to solving are the following. First, you're going to solve what's called the associated homogeneous equation. And that's just where you zero out the f. Now, again, we don't even know how to do this, but I'm giving you a high level overview. We want to first solve this associated homogeneous equation. We call the solution, the general solution to this, the complementary solution. Call the solution, or denote the solution, x sub c. The c here stands for complementary. Okay, cool. And then two, find any particular solution. This should feel very familiar. Which we'll call x sub p. Then, the general solution to this equation, x prime equals px plus f, is x equals x sub c plus x sub p. Okay? Now, I won't go through the details and check this. You can check this yourself, okay? What I would rather do here is show you how this kind of worked in practice in a previous example, actually, that we have computed. So in the past, we looked at the following system. X1 prime is equal to x2 minus x1. Sure, I'll write it like this. x2 minus x1 plus t. And x2 prime was equal to x sub 2. This is a first order system of differential equations, linear. And notice that it's non-homogeneous because of this plus t that we've got here. So if I want to write it in this form, how do I do that? I'll write it in the following way, in the sort of matrix notation. This becomes x1, x2, and then we're going to take the derivative of that, okay, is equal to, now what's the matrix of it's going to be, so x1 prime is equal to negative x1 plus x2. I mean, I'm going to write it in the other order to see the coefficients of x1 and x2. That's going to be negative 1 times x1 plus 1 times x2. This second equation is going to be 0 times x1 plus 1 times x2. So here's the 2 by 2 matrix that we get. We're going to multiply this by x1 and x2. The vector x1, x2. And then we're going to add to this our f. The f in this case is going to be t0. And because that vector there is non-zero, this is a non-homogeneous linear system. Okay, so to be absolutely clear, what's happening here is x prime, this is my x prime, here's my p, here's my x, plus my f. Hopefully all of this is clear. Alrighty? Now, working through the steps, okay, of this. I'll suppress some of the details. You can go back and look at the previous example. This happened when we were talking. I solved this system when we were talking about systems of differential equations. You can look up that video. If I'll just write down what the solution is. So the solution to the associated homogeneous system, that is to say x prime equals px. I'm just going to show you what this is. We're going to denote this x sub c, and what this will be, maybe I need some more room here, is going to be some constant which I'll call c times, let's see, what does it end up being? It ends up being 1/2 e to the t here, okay? And then down below we have, in the second entry, e to the t. Yeah. Now I called it c in the when I solved this in the systems of differential equations video. I'm going to call it c1 here, the constant. I'm going to call the second constant, I called it d for Donstant in the original video. I'm going to call it c2 here. And this is c2 times, what does it end up being? X2 ends up being 0, and this one ends up being e to the negative t. And then 0. This is it. You can check. You don't need to believe me. You can check that this solves this the associated homogeneous equation. So what is that associated homogeneous equation? It's where you zero out the f bit. Okay? Take the derivative of what we got here. Let's see, is that right? I think it's right. Well, you can check, okay? I'm not going to do that check. Maybe I'll do it, off the video to make sure that this video is actually correct. But I'm going to just push forward, okay? That's my x sub c. Now, what's an x sub p? I don't expect you to find this either or know how to do this either. I'm just going to tell you what it is. X sub p is going to be t minus 1, 0. Okay, t minus 1 times 0. So in other words, when I plug this in, t minus 1, 0 plus 1. Yeah, it totally works, huh? Do you see it? Plug this x sub p, plug this into this equation, or into this one, and you should see that it works. 0, 0. Yeah, totally. Cool. Okay, so this really is a particular solution to the non-homogeneous solution system. And so what I'm saying is that you can take x, your general solution to the purple thing, to be x sub c plus x sub p. Just literally the sum of those two expressions. C1 times 1/2 e to the t, e to the t, plus C2 e to the negative t, 0, plus t minus 1, 0. Now, if you interpret this, okay, in the language that we had earlier, what this is saying is that x1 of t, the solution to the original differential system of differential equations, is going to be c1 times 1/2 times e to the t plus c2 times e to the negative t plus t minus 1. Why? How did I do that? I just summed up the first entries of all of these vectors. And then that's going to be my x1, because x, remember, is x1, x2. X is x1, x2. And x sub 2 is just going to be the second entries. So that's going to be c1 e to the t plus c2 times 0 plus c1, it's just c1 e to the t. Got it? Okay. That's enough for this. In the next set of videos, we're going to begin talking about eigenvalues and eigenvectors, which is a linear algebra concept, which is central to our method for solving these systems of linear differential equations in the situation where we have constant coefficients. Okay, see you in the next one. Bye.